Hi everyone, welcome to Team 28's Senior Design Demo Day presentation for building a 3D printed surgical inserter to deliver microelectrodes to the deep brain for symptoms of Parkinson's disease. This project was conducted by Dennis Keibel, Eva Fritz, and Sunshine Snyder Drysdale under Dr. Martin Hahn. Our main objective for this project was to improve the design of surgical inserters for deep brain stimulation by making it user-friendly, highly accurate, and minimally invasive to the patient.
Deep brain stimulation, or DBS, is targeted electrical stimulation of a portion of the brain, in this case, the subthalamic nucleus, to treat Parkinson's disease. A decrease in dopamine in the brain causes the subthalamic nucleus, or the STN, to act as a stop and decrease mobility, which is a symptom of Parkinson's.
When redesigning prior iterations of the surgical insertion device, accuracy and user-friendly controls were a main priority. Past iterations allowed for horizontal movement of the inserter during insertion, which resulted in lower target accuracy. As the STN is very small, decreasing this movement was crucial. The addition of half rings and decrease in diameter of the cannula, base, and mover wells served to only allow vertical movements of the inserter during surgery. Areas that previously held instrumentation devices were removed and implemented into prior design aspects, such as creating a motor holder in the knob that controlled its vertical movement. Additional changes for housing instrumentation devices will be included in future iterations as testing moved to simulations.
Because we mainly focused on the software side of things, that's what I will be talking about for the instrumentation. We had to simulate a force sensor reading, a displacement sensor reading, and we had to simulate the Arduino's analog to digital converter response in a software called TINA by Texas Instruments. The force sensor was represented as a clipped sine wave so that only the positive portion of the wave was used. The displacement sensor was modeled as a linear piecewise function. Both the force and displacement sensors work the same way, so I will only describe how we achieved the force sensor reading. The clipped sine wave is an analog signal that needs to be converted to a digital one so that it can be interpreted by software, which cannot use analog. This is where the Arduino comes in. Arduino has an analog to digital conversion ability built in. The analog signal goes into one pin at the bottom and out comes a digital signal at the top. To interpret this digital data, we use the digital to analog converter to convert it back to analog. This is the waveform you see on the right. Why would we convert the input signal to digital only to convert it back to analog? At a lab bench working with a true sensor, you would not know what the analog signal looked like until you converted it to digital and then interpreted that data graphically. We merely did the same thing in real time.
This was our general process of accomplishing a tissue model. We had 3D printed out positives to use for the forming of the molds, which would have been made from UMU 30 silicone rubber. We would form the container of the mold, place the 3D printed positive within, pour in the 2-part mixture, and let it set for a day. Once formed, the mold would be extracted and the 3D printed positive removed. Agar and gelatin could then be poured into the negative to create the STN and hold brain analogs. Insertion simulations were conducted using ANSYS mechanical explicit dynamics for insertion at 10 mm per second into 2 discs of simulated brain tissue, an STN. Total deformation result displays that brain material easily parts away as expected. Total stress is very important, as the stress on the brain analog needs to consistently be below a certain threshold. Assuming a contact area of 1 mm squared, forces of less than 13 millinewtons were exerted onto the tissue analog. Total strain demonstrated the elongation of tissue at the tip as the inserter continues to push through the material.
The videos on the left and right show the real-time data acquisition of the displacement sensor and force sensor respectively. The signals are measured by probes at the input and the outputs of each circuit. Real-time data was necessary because feedback about the force and direction of the inserter in the brain ensures that the rod will reach its target while minimizing brain tissue disruption.
Overall, we have found significant results and made great improvements to prior iterations of the insertion device. Feel free to pause and read this summary of accomplishments we have made over this past year. In the future, we would like to implement physical testing to compare with our simulation results. Additionally, many planned changes to our insertion device involved housing instrumentation so that it was user-friendly and usable. We would like to implement those changes in the future once a physical prototype of the instrumentation is constructed and measurements can be obtained to then create a full automated prototype. Finally, we would like to continue with our brain model testing by 3D printing the half brain, creating the UMU mold, and testing the full prototype of STN insertion on the model. We would like to thank our faculty advisor, Dr. Martin Hahn, for all of his guidance and support throughout this project, as well as the BME department and senior design instructors for all of their help throughout the past year.